Yeah, we're a little behind schedule, so we're still on multi-body systems. We're just going to finish talking about dynamics today. And then we can talk about where we want to go from there. Yeah, so we were supposed to be in atmosphere already. And that really didn't go to plan. But that's kind of like how life goes. Sometimes life do be like that sometimes. Hi, David. How you doing?
How about you doing?
I'm doing amazing.
How are you feeling about the Dodgers?
Boy, you don't know. You don't know. So one of the things is I really wanted them to win in LA. I thought that was really fun, like go to game 6 or something. And then I was like, okay, so what do I prefer? I prefer to go to the parade, or I prefer to watch them win. Parade, obviously better. So we're just going to take here. Oops. Next week I'm going to be in Paris. So we're going to have a conversation about what instead. So you have a homework. Do you look at it? Okay. So almost everyone got the same part of 3 wrong. And I'm just going to write out what my thinking is so that you can try to emulate that same thing. Okay. The first thing is in 3, right? And I'm not going to draw everything out again. I'm just going to kind of talk through it. I think it was for 3B, you were asked to find the work. You remember that? You remember what the work was? You didn't memorize it?
Integral of the force, right?
Yeah, no, sorry. Just like what the answer was. So here's what the answer you got, the majority you got, is that it looked like this. 3 halves g m little m over r cubed times x squared. That's what almost everyone got. Okay? And then it all went haywire. And some people got a million kilometer times. And some people got, 100,000 kilometer times. And I think it's very straightforward. Okay? So the thing that happened is we have to make a couple assumptions, and then we have to pay attention to what we actually were calculating. So what does the work represent again? You were saying it in terms of an integral. What did you say?
Force.
Force.
Yeah. Force that over.
DL, right. So force over some distance DL, right? And what we mean by that is that this is how much the force is applied over some infinitesimal amount. So what do we calculate? How would I define this physical force? Or work, I should say. Like what did I calculate in 3D? So this is again, I don't remember the homework because you didn't memorize it. That's fine. I'll memorize all that. Here's the moon. Oops. Here is some distance x. That's r. Okay. Okay. So what did I calculate? What was I trying to do in 3? Do you remember? Problem 3 of homework 3.
Was to calculate the size of the tides.
Size of the tides. So we found the work done by who?
Done by the tidal forces.
Right. Who causes the tidal force? The moon, right? So the moon is creating this tide. Okay, so that's in my mind now. So if I'm thinking about it in terms of a budget, let's say a budget at home. I make $100, I can spend 20 on gas and 10 on fast food, et cetera, right? The work here is all of the energy I have available to me to raise tides. That's it. So if I asked you, pick something up how high can you pick it up off the ground in terms of energy? Let me ask you a different one. Let's say I take the potential energy just for us in this room, pick this up. How much potential energy do I have? Gravity, good. What, I'm gonna put that here. Mass.
Height.
Which one? Oh, yeah, height. Yeah, okay, good. Yeah, like that, right? mg. Good. So that's all I have. So I can set these two quantities equal to each other. Right? Now I want to find out the height of the tides. That's what it is there. And I think most people got here. That's perfectly fine. But then they forgot how to write h. Because h is hidden over here as well. Now the first thing that we have to say is that this is really mg x minus r. Right? So I have x here and I have x there. So let's rewrite all of this. Okay, this is the stuff that is saying the energy equivalence. Let's rewrite it. And I'm going to go ahead and I'm going to drop the m. There's an m here and there's an n here. Let me get rid of them. So let me just write this as 3 halves gm over r cubed. And I'm going to put that into parentheses. You'll see why. X squared. I'm going to move the x over. I'm going to say plus g minus g times x. Oops. Okay. I'm going to move the r over. And that's going to be plus gr equals. Good. And how do I solve that?
Could you use the quadratic formula?
Okay. And that will give you an answer that doesn't suck. Okay. The reason that you need to know this is because you're going to use something very similar to this in the future work, right? Okay. This is like a generalized form, right? We haven't done anything unique here in talking about the mass of the Earth, mass of the Moon. All we're talking about here is these things like G, surface gravity, mass of the Moon, distance away.
For G, for little G, is that surface gravity of the moon or is that surface gravity of the moon?
Good question. Which one is it? Let's go back to here. Where did we get that? For the Earth, right? That would be like if it was in this room. How much energy do I have to pick something up? Is that fair? Cool. It's okay? Yes. Yeah. You want this or you want this? Okay. I'm doing great. Dodgers are 1-1 away from the World Series. They go to Paris on Saturday. So now we have a decision to make. Because I won't be here. I believe Katie or Dr. Wimberly can teach on Tuesday. But I don't know what to do about Thursday yet because she needs to go to San Francisco and I will be actually on a plane, completely unable to contact you. So you can do one of 3 things. Okay. We can pre-record the lecture. You can just watch it on your own. We can do it at a different time, like this different day, like Friday, or we can skip it. So if you want to do pre-record the lecture, different time, skip it.
Do you know what we're talking about today?
Well, that'll depend on what we talk about today. So we're a little behind schedule, obviously. We're going to finish talking about multi-body systems. So we'll talk about how to get asteroids from one place to another. And by that process, talk about how to get rockets from one place to another. We'll talk about three-body systems and Lagrange points, how we set those up. If we make it to the end, there's not going to be slides today, but there's a lot of math. So if we make it to the end of today's slides, then we get to have a discussion about whether we would prefer keep talking about rocks. So we could talk about meteorite classes and moons of the giant planets, or if we finally want to start talking about fluids and atmospheres. That's the choice at the end of the day. Okay. You want to tell me what you want to take at the end of the class? Okay. All right. Here it is. Multibody system. So we're going to talk about transfer orbits. I say the word simple, not because it's easy, but because conceptually they are straightforward, right? So mathematics is straightforward. Pulling it off, obviously, is difficult. We're flying around in space, okay? And similarly, we talked about the two-body potential before. We'll talk about Lagrange points when you start moving stuff around, right? And this is before stuff starts moving, okay? So here's the messenger spacecraft going to Mercury. It has 6 gravity assists and 5 burns. So let's see if we can find ourselves. There's us launching. And you'll see this very funny symbol here called C3. You'll learn what that means later. Okay, it's this number. So you launch. And you start on this blue line. Okay, blue line, blue line, blue line. And then, wait. Oh, here. Okay. We go around once. Okay. We catch up to Earth and we do a flyby. We get really close to the Earth and we let the attraction of the Earth change our velocity. And then we go in. How did we go in? Remember? Speed up. Okay. So you speed up. Here is DSM-1, that means deep space maneuver. So this is a burn. So we do a trajectory course maneuver. We come down here because we want to do a second burn here, DSM-2, in order to hit Venus. We want to go farther into the gravity well. We got to gain speed. All right. And now, this one's fun. We fling ourselves way out past the Earth. Earth's not there, so it doesn't matter. And then we go back in and we hit Venus again. And now we have enough energy. So now we're on this green line. This green line now goes in. Okay. And then we go to the okay, orange lines. And what we're doing now is we're doing multiple Mercury flybys. And each one of those we're taking. So this is how you get there. So this is the path. Earth, Earth, Venus, Venus, or Mercury. Cool, right? Okay, so let's figure out how we do this. Okay. How do particles change their orbit? Sometimes you smash into stuff, right? That's like, we see that in the asteroid belt. We see the effects of asteroids grinding up, that there are more small asteroids than large asteroids because you can't put them back together. You can only break them apart. So as you hit them more and more, you have collisional grinding, which produces more sand-like features. Then it produces big boulders, right? Okay. So sometimes we do this on purpose. So sometimes we give spacecraft energy. And in order to do that, we use the moving Twitter law in order to do that. Right? So here's a good example. Let's say this is an object, and I'm going to give it some delta V here. Okay, get it to go out, and then another delta V to change the orbit. We talked about this equation. I don't know if you remember this one. This is called the Viva equation. So what this one said was for a two-body system, you can describe the motion of that second body, the orbiting body, completely, because at every point in the orbit, you know, if it's an ellipse, you're going to be able to point to where the ellipse is, right? So basically the thing that we need to do is we need to specify the orbit by this equation, and then we can go between different orbits just by changing A. Okay, so let's show you what I mean by that. Let me show you what I mean by that. Here's the Earth. Here's some circular orbit. Let's say it's a low Earth orbit, so like not to scale, but you know, like 400 kilometers of the surface. Okay, and I want to go from this point here, that's at some distance, R1. Okay, and this R1 happens to be equal to A1. R1 equals A1, right? For the circle. Okay. Now the next thing I want to do is I want to speed it up. And I want to go on this path here. Can I go any arbitrary shape? Can I go like this? No. What's the curve have to be? Speed, yeah, speed's got to start perpendicular to it, sure. But what is the shape of the orbit always going to show? Right? Always got to be elliptical. Of course, circular comes in with that. Okay. So, of course, we can think about this as the section of a much larger elliptical orbit that is not taken. Right? And so instead, what happens is I take this segment of the elliptical orbit out to this point. Right? And now I change the orbit again. And now I'm going to go this way, which is perfectly okay. It's not tangential, right, David? So this one here, I can point out of the line of sight and change my direction. But now I'm going to go. I'll imagine that that's perfectly circular. Oh, and also. Right. So this one I would call R2. And of course, R2 is equal to A2. And at this point here, that is still R2, no? But for this ellipse, let's call this ellipse has a semi-major axis here. That way, right? Let's call that AE. Okay. AE. How does AE compare with A2? Let me ask a different question. How does AE compare with R1? Or A1? Yeah.
Basically, the radius of R1 is the radius of mass supply.
Yeah. My question is, how do they compare? Which one's bigger? AE is definitely bigger, right, than R1. Is AE bigger than A2? Do you agree? Okay. Right. So what I did here is I started on a circular orbit. I changed my orientation, my velocity vector So I was following the path of this big ellipse, and then I changed it again to get onto the big circle. But all of those individual paths are sections of an ellipse, right? So this piece here certainly doesn't look like it on its own. When you draw the whole ellipse, you're like, oh, okay, that makes sense. Is it always the case that the larger ellipse is bigger than the bigger circle? And in fact, that's not the one I've drawn here, right? So here I have small circle, big circle. Now, of course, this small circle is not oriented. Off to there's a little bit of eccentricity. But this here, right, as I think about half of the 7-meter axis, it's almost covered, right? Maybe smaller. You can use different combinations of orbits. So when folks go and they work for a place like Lockheed Martin, where your job is to fly spacecraft from point A to point B, real job, you have something called the spacecraft toolkit. And you can't just go left, right? You have to calculate where your new trajectory is going to go using these types of equations. There's no streets. Okay, that makes sense. We're going to talk about the most easy way to do this. This is Pullman transfer. All right, let's figure out how to do a Holman transfer. This is the most energy conservant way to go from point A to point B. Why do we care about conserving energy? Woke liberal media in our classroom, is that the problem? No? What is it? Save money. Fuel is fucking expensive. And sending fuel to space, it's dumb. Right? How much does fuel cost? Or how much, sorry, is a kilogram cost when you send it into deep space? You know? What was that? Yeah, it's about $1 million per kilogram. So if Jahir comes up with a concept and he's like, okay, I can do it, but I need $80 million worth of fuel. And Dante comes up and says, well, I can do it for 50. Guess who's getting the bid, right? Dante's going to get the bid, and so then Lockheed Martin makes a lot of money, right? So let's think about how we would do this together. Okay. We are going to take two circular orbits, the same way we did before. But instead of just going from here to here, maybe the closest path actually may not be the smallest amount of energy. Right? Where does the energy come from in the spacecraft? What are the things I have to do? Walk me through the steps. I'm in orbit around the Earth. Okay, fly the thrust. Okay, hit the booster. Call that DSM-1. Okay, deep space maneuver 1. Now what? No, we're hopefully outside the atmosphere. We're not outside the atmosphere. We're in real danger. We're already orbiting. So we're going around, and this is, by the way, going around like 30 kilometers per second. So we have to be high, or like 1,000 kilometers. We hit thrust, and we leave this circle. Now, keep going, keep going. Earth's still pulling. Right, let's not imagine that there are any other planets. There's no other satellites. I'm not going to a moon. I'm just changing my orbit. Headed out, I'm headed out, I'm headed out. Okay, and I'm slowing down because I'm getting farther from the Earth, right? Now what? Okay, good. Let me fall back in. Okay, so you need two deep space maneuvers, right? And in those two cases, we need delta V. We need to change the velocity, right? Make sense? Okay, how much do we change the velocity by? Let's go back. All right. Hurry. Jim. 2 over R minus 1 over A. Okay, and you're telling me that I can do all of space travel with this? You can. Yeah. Okay, let's use it. Let's use it. Let's use it. Okay, so now we have to be careful, right? We have to look at the naming there. So let's use the naming characteristics that we did before. Come on now. Okay. So we have 2 circular orbits, radius R1 and R2. We are going to transfer from the smaller one to the larger one. Now, of course, I could run this backwards. I could lower my orbit easily. And we're going to imagine that happens instantaneously. My velocity is just going to click and be different, right? Okay. So I have a couple things I've written here. Here's F, right? F is what again?
Basically, it's stretched apart, the ellipses.
Yeah. Well, no, that's the E, right? Oh, this one here is talking, when we wrote these out, we were like, this is one plus epsilon would be the perihelion or aphelion distance, depending on if it's plus or minus, right? So that would be R1 or R2 for this ellipse. Now notice here, the Earth's up the middle. So this distance here is R1, 1 minus E. And this distance, R2, is 1 plus E. Okay. We know that the 2 times the semi-major axis is the sum of them. That's the definition of the semi-major axis, right? Okay, now we've done our delta. We have all the work. Okay. You believe me? Okay. So I want you to find the following 3 velocities. Okay. Velocity before DSM-1. Now you're going to split up. You're going to work together. Okay. Velocity before DSM-1 in small circle. And then you're going to have the velocity after DSM-1. Right. Then I travel all the way to here. And now I need the velocity. I'm going to stop writing the word velocity. You okay with these ditto notations? Velocity before DSM 2, that's going to be up here, deep space number 2. And then the velocity after. Is that fair? Okay. So I think to do this effectively, I think you should work together and split up which one you're taking, but first talk as a little group and see if you can do, right? We have the information, theoretically. Theoretically. You can keep everything in terms of R1s and R2s. Don't try to solve them. Just want to write the most basic version down, and then we'll expand it. You want to help anyone? I guess. That person? Who got 40? Okay, get it? Yeah. Per chance? So 1 and 4 are the most straightforward. Why? They're circular. And what's the orbital velocity for a circular orbit? Third of GM over R. A is R. Okay. 1 minus R. 2 minus R minus 1 minus R is 1 minus R. Okay. So it's just GM over R. Right. Right. So the inner circle is what? Yeah, GM over R1, right? So I can write this like this. B 1 is square root GM over R1, right? What about 4? That? Oops. That? Start at the middle. Okay. Okay, what do I put in here? 2 over R. What's the R? R1, good. What is 1 over A? What is A? Good. R1 plus R2 over 2. Another way of writing that, I could say 1 over A is oh. Let's change this. Okay. Make this 2 over R1 plus R2. Now, am I allowed just to immediately subtract the denominators? Bottom parts? Yeah, good. So don't fall into that trap and try to get rid of the 2 R1s, right? But the 2 comes out. That's perfect. What about this other one here? V3.
Yeah.
Good.
Minus 2 over R1 plus R2.
Good. Okay, now we're cooking. Now we're cooking with gasoline. Right? We can make some simplifications, of course. Bring the 2 out. So I could call this one 2GM. And then in here, I could rearrange this, right? I could multiply tops and bottoms if I wanted to. But I'm just going to go ahead and leave it like this. 1 over R1 minus 1 over R1 plus R2. And I'll show you why in a second. And similarly with the other one, right? But just ditto, but just with this is 1 over R2 instead. Right? All right. That fair? Where's the one that's fast?
I'll see before these and 1.
Yeah, same before this. You sure? Think the last one? Okay, let me ask you a different question. How does V4 and V1 compare? Which one's bigger?
V1 would be 1 significant.
Why?
Because since our radius is on the denominator, the smaller number on the denominator is on the bigger.
Okay. Good. So let's put V1 over here. And I'm going to put V2 over, or V4 over here. Actually, no, let me put these next to each other. So you're claiming that V1 is larger than V4. Is that correct? Yes. All right. Now let's think about V2. Where does that fit here? V2 is going to be faster than V3. You sure about that? What?
The R1, which is the well,
okay, so if I don't even look at this, if I just look at the ellipse, right, then I know using Kepler's second law that this is going to slow down as it moves away from the planet. So I know that the V2 down here has to be bigger than the V3, right? Okay. How is V1 and V2 related? V2 is bigger because, so what's the square root of 2?
1.5.
Yeah, 1.44, 1.5 is about 50% bigger. So now the major question is okay, so we have a competition between terms. This term looks exactly like our other term, but this is about 50% increase. What's this one like? Okay, so 1 divided by number. Which of these two terms is bigger?
The one of them.
This one's bigger? This term?
The number would be small.
This term on the bottom is bigger than this, so therefore this term on the right is small. Okay, so this number minus a number. Okay. That's a good question, right? Don't know exactly whether or not this 50% increase is always going to be bigger than this increase, right? Okay. Fine. One. I put these in here, by the way. You can look at those later. That's not important. Okay. Here's the V's. You just did it. Yay! The thrust that's interesting enough, you have to speed up at both locations. You have to speed up to leave the orbit, and when you arrive at the new orbit, you have to speed up again. Right? Okay. And so you wrote that one. That one's straightforward. You wrote this one here at the bottom. That's V4. This is right after. I've used different letters. I apologize. This is right after the burn, and this is right after this. Right? And here's how they're written. VF final is certainly greater than this one. And this one here is greater than this one. The speed up. And I'll show you that. Okay. So one thing that we need to do, of course, this is a three-dimensional problem. You have to speed up without changing the direction. And ideally, you'll also create circular orbits. So here's how you change the momentum. That's delta P. And we're just going to take these two versions, right? Whether it's these two or these two. That delta P is really the delta V. Right? So think about this one here. Is your V2. Subtracted away from your V1. So can we do that? Can we subtract this one from this one? What do we get? Let's do delta V is equal to V2 minus V1. You may find it helpful to do those. I guess it's actually not how I wrote it on the board. Leave it in square root form. I apologize. Don't try to simplify it. Right. Right. Yeah. Root of G times M.
Then quantity of 3 over R.
Where's the 3 from? The 2 over R1. I'll take that. Okay, next. Okay. So some folks might 2 out, but that's okay. That's the first one, right?
Yeah.
And then I'm subtracting off. GM R1. Okay, interesting. So I see a lot of stuff that I like. You know, the GMs, like really attractive to me. Pull them out. If I could do something like this. And then I could multiply all of these together. I could have the square root of 2 over R1 minus 2 over R1 plus R2 minus 1 over R1. Right? Oh, that's gross. Okay. Any way to combine anything else here?
Combine
You could pull out an R1, right? Yeah, so there's an R1 here, an R1 here, but there's what?
I personally would have.
Yeah. So this one's annoying, right? What? Well, remember that we can be magicians here, okay? So there's an R1 here, an R1 here, and an R1 here. So these ones clearly we can take out. That one we don't have a problem. So let's change this really quickly. Square root of 1, by the way. Good. That's just gonna be 1. I'm gonna put the 1 over R1 here. Okay. That means I took this one out. I had that. So that becomes a 2. Okay. What did I do here? Let's get our R1 out there. So remember, let's write it over here really quickly. R1 plus R2 is the same as R1 times, you're gonna hate this, 1 plus R2 over R1. But it counts. Right? If I multiply that in, you get the same thing. That's not witchcraft. That's just trickery. So I can put this down there. Right? You hate it? Okay, good. All right, well, here it is. And you can distribute out those R2s if you want. You can rearrange them. That's what I did. So you start with something like that, you end up with that. Everyone's upset. But you can tell whether or not this is a positive or negative quantity, right? So this thing here, what did this thing represent again? Mg over R? V1, right. So this is our initial velocity. Very good. Okay, so now the major question is this thing speeding up or slowing down, and can I prove it? So R2 is bigger or smaller than R1?
Is bigger.
Bigger. So what is this? Positive or negative? Sorry, let me say that wrong. Bigger or smaller than 1?
You said R2 is bigger, right? So if you're adding R2 and R1, that's still going to be smaller than 2 times R2.
Right. Let's remember what R2 represents. Right? This is an ellipse. This is an ellipse. This is R1. This is R2. 2 times this value would be all the way down here. Always going to be much larger than R1. Except for if it was a circle, if they were the same size, right? That would be a little funny. What would happen if they were the same size? Well, if I go back to my values, okay, R1 and R2 are the same size, and this is R1 plus R1 is 2R1, and 2R1 over 2R1 equals 1, and 1 minus 1 is. And I don't need to speed up to get out of my circle because I'm already in the circle. You see? Wow. And I didn't do any work. It all came naturally from the fact that I'm just going from one ellipse to another ellipse. I'm crazy. Fucking freak, bro. That's how you know you did it right. You get shit like that. You're like, oh, okay, cool. Right? You put in those weird cases. Like, what does this mean? As I grow it and shrink it, do I get back the thing that I expected to get back? Right? If I make my ellipse huge, I'm going to have to speed up a lot. Does it make sense? If I make my ellipse small, I won't have to leave. Right? Okay. All right, there's the changes in the momentum. We tend to talk about this in terms of thrust. That's the force here. And think about it in terms of durations of burns. So what I mean by that is momentum per unit time. That's perhaps not unusual to the way that you think about this. Right, a force is change in momentum with time. But here, when we talk about the thrust force, you throttle your engines for a certain amount of time. And the reason why this really matters is, let's say you have folks on board, right? If you have folks on board, you can't be infinitely quick. Right? What does that do? It smushes them, Okay. You want your passengers to enjoy the ride. So you do need to achieve this change in momentum, but you can decide how much time you want to take it, right? And of course, you figure that out later. That's what. Is that fair? The time it takes to reach the final destination is half the orbital period of the transfer orbit. Does that make sense? That's intuitive, right? You're going on an elliptical orbit, you just have to go on the ellipse. So you shoot, you fire your rockets, you just wait until you get to the place you're going, and you fire again. Good. And of course, we can just write that in terms of Kepler's spin. Okay. Generally speaking, close encounter between asteroids just give you this momentum boost, right? And whether that is by passing nearby another big moon, or passing by another asteroid, or by being in resonance, right? You are going to develop small changes to your velocity. That's either going to send your orbit in, going to send your orbit out. So, for example, let's say you're on a very elliptic orbit, going to do this big ellipse, and you're getting very close to the sun, getting close to the sun, and yet one day you happen to pass by Mars, and Mars pulls you, speeds you up towards it, and it circularizes your orbit. And now you live out by Mars. That's just how these types of things work. Sometimes they can work in the opposite direction. Say you're best friends with Mars, and you get too close to something else, and gives you a ton of energy and kicks you out towards Jupiter. That can be horrifying. Or if you're going along, let's say that table is an asteroid and I'm Mars. If I catch up to it, I can pull velocity away. What happens if I pull velocity away in this scenario? Let's say we're both in a circular orbit. Decrease, right? So now this thing starts heading towards the sun. No? So that's the funny thing. If you ever watch Gravity, with Sandra Bullock. Okay, so Sandra Bullock has a problem. She's in orbit. Okay, let's say you're detached from a space station and you want to go grab some stuff in order to survive. Like you don't have your little booster jet. Which direction do you point? You want to go over there. That might not be the right way to get there. Right? Let's say it's not just right in front of you. Let's say I need to get way over there. The best way to get way over there might be to slow down. Right? Sends you up that direction versus speeding up, sends you the other direction, right? Okay. So this happens constantly, and we'll see this in the asteroid belt. You saw all those bodies, for example. That's how they get scattered around. Yeah, I don't think I care. You can do this map if you want. You can write it out. Prove to yourself that you know how to do this, and may be helpful. You want to see it on the board? Are you good? So let's slow down this asteroid, and you can show, for example, how much damage this would cause if you slow it down by 4.6 kilometers per second. Let's say the orbital speed was 14. Okay. A small body would have to. No, hold on. I don't care about this right now. Let's talk about the next. This one. Okay. We don't have very long to do this. We're just going to kind of think about it in the context of the three-body system we were talking about before. You have two bodies orbiting each other, and we talked about why we might want to set this up. Say, for example, Saturn and the Earth, or sorry, Saturn and the Sun, or Jupiter and the Sun. You have two bodies that basically the only things they care about are themselves, right? And then you might have little stuff that goes around it. The sun. Oops. We don't care about how they're recorded. But if I'm a little test particle, say I'm here, Mateo, okay, how am I going to move? Yes. Sun, okay, good. So now I go towards the sun. They start going really, really fast, and I get flung out super fast. Oh shit, now I go around Jupiter, right? But now I get flung out this way. Oh god, and then I go this way. You see how it becomes chaotic right away? Okay, so this is the first example of what we call the restricted free body problem. We are not going to move Jupiter or Saturn in this reference frame. Now, of course, Jupiter does go around the sun. Why is it Saturn? Jupiter is going to go around the sun, not Saturn. So in order to make up for that, you're going to have to rotate the reference frame. Is that a problem? No, you're very familiar with doing this with tides, right? Your favorite thing to do in the world is to just add a little gravitational rotation, right? So essentially, we're going to have something like a gravitational potential. We'll talk about it in terms of the same U's that we talked about, but here we'll call it phi. And it'll be a specific potential. So it's going to be the potential energy per unit mass. Okay? And it's going to have a fictitious force, okay? Such as the centrifugal force. Right? That's from the fact that it's rotating. Okay. Oh my god, good morning. Let's try not to go to sleep already. Okay, so here's the two bodies, right? Here's M1. Here's M2. We're going to put them at arbitrary distance here. Of course, you can place M1 at the center. Here's the center of mass of this. These two are the ones that have mass. We are going to ignore the mass of this body. Okay, imagine that no mass, hence the word restricted. Okay. They're not going to be attracted to this. They're only going to be attracted to each other. They go around. Everything's fine. Here's all the angles. Here's all the distances. Some major axis between them. R1 plus R2. You're quite familiar with that. That's the center mass. Right? And so here are the things that I really want to think about, because when I start to do this properly, this is the one I care about. If I have my particle. If I want to see where my particle is going to go, what does S1 represent? The distance from M1 to my particle, right? And what's S2? The distance from the second. Second mass, good. Okay, so if I want to write my gravitational potential, not the force, the potential, it's pretty straightforward. So I already divided by the mass of the particle, so I'm going to drop little m. That doesn't exist. So just minus g, m1, potential, divided by s. Easy, right? M2, s2. Easy. And then something over here that's going to bother me. Okay. Okay. Pretty straightforward, right? Can you use potentials to find out motion of an object? Yeah, how do you do it? Yeah, so this will be, energies and works they're very similar, right? How do you get down to kinetics? How do we get to try not to give it away by saying? How do we get the position and the velocity of the particle from something like a potential? That's so weird. Okay, I have potential right here. Remember, I told you that even though mechanics sucks, we can use something called the Lagrangian for the Hamiltonian. Oh, but I hate those good ones. So what are they? Oh, I said I hate them. Okay, the Hamiltonian is an energy statement. H equals General. You don't have to look in your notes. Kinetic energy plus the potential energy. You're done. That's it. How could that possibly be true, Grisman? I'll show you. Okay, so Lagranges are great because if you can find the potential, right, and you can write the potential in terms of x, y, or z, then you can write the kinetic energy, and you have the velocity and the position. Good. So the only thing I have to figure out is centrifugal, the fact that this thing is rotating. But that's not horrible, right? We kind of did that already. So we had the potential energy. We could think about it in terms of the centrifugal force. It had mv squared or m omega squared r. You just integrate, and that gives you the work. And you can just add that work into the potential. If you're thinking in your head, wow, I've always had this like force term, say like a frictional force. But you could never create something like Hamiltonian from it. Well, you can. Just take the force term, integrate it over whatever distance, and go ahead and slap it into your potential energy term. Right? So that's the source of energy. So all this is doing is it's accounting. This is the velocity. These are the different ways I can hold energy. And if they're not included here, they don't exist in the problem. Right? Notice there's no electromagnetism in here. There's no quarks, right? Only thing that matters is the fact that it's moving, that it's attracted to two bodies, and that the whole room is rotating. Right? And then we're done. We have this beautiful little term. Okay. And of course, you can write here the omega squared in terms of this is the angular frequency we said of the rotation. And of course, we would hope that the rotation would be equal to the period. Otherwise, they wouldn't stay in the same place. So we can write this potential just like we had before. But it's going to look like this. 1/2 omega squared, but instead of r, it's r squared because the integral of r is r squared. R squared over 2, right? Or yeah, 1/2 r squared over 2. So 1/2 r squared. Yeah. That's all I'm saying too. Good. So that's good. This is exactly what we had before. We just integrated. And it makes perfect sense for such geniuses. We think this is wonderful. We're just going to change some of this around, though. Because this thing here does not depend on the omega squared. Does not depend on any of the conditions, but the r does. The r is the location of the particle. So if I'm closer in, right, I'm going to be spinning faster or slow. Now, think about just a rotating table. Like physical distance. Rotating. My hands rotating faster than my body. Angularly, they're not. But which of the two is covering more distance? My arms. My arms are actually moving at a higher velocity than my chest. How weird. It's kind of counterintuitive because you don't really think about it when they're moving all together, right? The whole board is rotating. But if you had your two objects here, if you're closer to the center of rotation, you're not feeling the centrifugal force as strongly as if you're way off, right? Then you're being flung off the board. Okay, so that's why here we got to remember to keep this r squared. Super important. Because as you go out farther, weirder shit happens. Okay? Okay. So these are very intuitive. You know, you're attracted to one, you're attracted to another. This is pulling you in. Okay? This thing here minus, okay? This thing's flinging you out. That makes sense? Here's what it looks like. It's pretty sick. This is the potential. So this is an X and Y. Here I have M1, which is 5 times the mass of the sun. That's here. And I have M2, which is 1 mass. So this is a binary source. A, the distance is 1 AU. So this is 2 AU in the negative, and this is 2 AU in the positive. So make a little box. And here's the places where I can live as a particle. Okay? All of these, what I'm showing you, are contours of constant gravitational potential energy. So the way to think about that is to imagine that what I'm drawing is a hill. Okay? So where the contours change rapidly, right? I might have like, this would be the same. I draw this properly. I'm not gonna be able to do this live. but here, this is like the flat top of a mesa, right? And then where the lines are all bunched up, this is falling fast. That's this part. Right? This part here, flat mesa. Whereas if I go in this direction, it's much more gradual slope. Until I get close and then I fall. Right? So like, you can all read contour maps again or no? Okay. Now, let's say I have a specific amount of energy. Let's say I have avocado toast amount of energy. Okay, that permits me to not go up or down in energy. Suddenly, I'm here. I'm on this plateau. I'm not allowed to go down. Okay, so I just go around this plateau. You ever seen that before in your life? Yeah, what was that? Okay, now let's say I get more energy, and I can go into the second contour, and now I can explore all of this space. What's that? See? Okay. This one here, you just like sit at a saddle point. You'll notice that it's a little weird. This is an unstable saddle. So if I get just a little push, I fall into either one. It's stable this way, left, right. So actually spacecraft will do this. They'll orbit this way. Because if they orbit this way, they'll fall. This one here, stable or unstable? Unstable what? Yeah, so this one here, look at the contour. So this falls in this way, and it falls down this way. So it's another saddle. So this is falling down, down. And so if you just give it a little push, it's going to roll down the hill. What this one? Unstable, right? Fall, fall. What this one? What? It's stable, yeah, it lives within here. Now, if it gets too far, unstable, they're still at the top of these hills. So all of them are inherently unstable if you give them too much of a perturbation. Okay. Is that fun? You'll be able to do that at home? I hope not. Did you say that?
Probably not.
Okay. Yeah, we'll try to finish this at the beginning of the next class. I didn't think I'd get through all this, and I didn't. So tell me what you'd prefer. Do you want more rocks? You want to talk about the moon and asteroids and comets and shit? Or would you prefer to start talking about atmospheres? We only have 5 minutes left. Atmospheres? Sorry, rocks. Sorry, not sorry. So all atmospheres from you 3? Do you have a preference? Rocks. Keep going. All right. Okay, fair enough. Do you have a look at the homework that started sooner rather than later? Let me know if the thing that we talked about at the beginning of class today helps.
Yeah. Oh, yeah.
That's up to you. You can tell me.
No,
No, you can tell me whatever. You can raise your finger. We can do it on Thursday. I mean, it's next week, so Tuesday will be normal. It just won't be taught by me. What? Pre-recorded? No, another time? See no class. Don't look at everyone else's. Everyone close your eye. Okay, now close your eyes and now do it like no one else can see but me. Okay. All right, now all close your eyes. Interesting. I don't know. Very mixed. I can throw a pre-recording on there. There also may be pre-recordings from the last time I taught this, but of course, me being able to record work always, kind of helps. So if you find that you're not really getting it, let me know. Maybe a combination of just like pre-recording and then talk about it after.
Yeah, because I still don't know what we're doing next week, because we're also a little behind. It's more math heavy. It's like the first. It's not.
Oh yeah. Interesting. Okay, I'll look at the next 3 classes, see how quickly we're getting through it. We abandoned the meteor stuff until later. We can go right into sort of the mathematics of light and how you heat up surfaces, why are surfaces hot, how do atmospheres get warmed, etc. We won't spend a lot of time there, but we'll spend enough. What's that? We're gonna finish up the one that we did started on Thursday, and we'll do that almost right at the beginning, and then we'll go right into just like pretty pictures of Cooper. Cool.